All right, section 7, repeated eigenvalues. So what if A is not diagonalizable? So yesterday we found solutions using eigenvalues, but we did it with the type that are diagonalizable, meaning when we had a multiplicity on one of the eigenvalues, we still ended up with two linearly independent eigenvectors. And so we were still able to do it. So what happens if you get a multiplicity on an eigenvalue but you only have one eigenvector, right? So how do we find a complete set of independent homogeneous solutions? So here's if lambda has a multiplicity of 2, but you only have one eigenvector, k1, we would have one solution. X1 is equal to e to the lambda t times k1. And then your second solution will be e to the lambda t times k2 plus k1t, where k2 is going to satisfy the equation lambda I minus a times eigenvector k2 equals the opposite in sign of k1. Okay, so let's do it. We're going to find the eigenvalues and eigenvectors of the given matrix A, and then find the general homogeneous solution to x prime equals A times x. All right, so here is example 1, where matrix A is this guy. Then your first step is to find lambda I minus A, which is lambda plus 1, a negative 1, a positive 4, and a lambda plus 5. And then our characteristic polynomial would be the determinant of this matrix. So it'll be lambda plus 1 times lambda plus 5 minus a negative 4. Well, that'll give you a lambda squared plus 5 plus 1, so a 6 lambda plus 5 plus 4, which will give you a 9. So that means I've got lambda plus 3 quantity squared. So that means your eigenvalue is negative 3, but it's got a multiplicity of 2. Yes, which we had that happen yesterday on the previous lesson on section 6's lesson, but it didn't matter because when we had a multiplicity of 2, we ended up with two linearly independent eigenvectors. So let's see what happens today. I have a sneaking suspicion that we're not going to get two eigenvectors coming out of this thing. All right, so we plug in negative 3 in here, and you would get a negative 2, negative 1, 4, and then positive 2. And we want to solve for when is this 0. And so I would need to go, I want to turn this into a 0. So 2 times row 1 plus row 2 would give me a negative 4 plus 4, negative 2 plus 2, and then a 0 plus 0. So that means my first row is still a negative 2, negative 1, 0. This row 1 says negative 2x1 minus 1x2 is equal to 0, which means x2 is equal to negative 2x1. So if I let x1 equal a, then x2 will equal negative 2a, which means that my eigenvector is, I'm going to go ahead and just factor out the a right away, 1, negative 2. Now, so we only have one linearly independent eigenvector, but then this guy had a multiplicity of 2. So that means we've got to use this strategy of finding that second solution. So what does this mean? Okay, so my first solution is e to the lambda t, so negative 3t times k1, so 1, negative 2. So I've got one solution, right? And our final solution will be a linear combination of this guy and the second solution we're about to find. Now, for the second solution, what we've got to do is find k2, find a second eigenvector that satisfies this. Okay, so for the second solution, we need to find k2 that satisfies this equation. Lambda I minus a times k2 is equal to the opposite in sign of k1. So we're going to find k2 that satisfies this. So lambda I, lambda I minus A was -2, -1, 4, and 2. And multiply that times K2. And that would equal opposite in sign of 1, -2. So we want to solve this, and I'm going to use a matrix to do it, right? I'm going to solve this equation by doing an augmented matrix, -2, -1, 4, 2, and then it's equal to, these are my K2s, right? -1, I'm distributing the negative in here, and then a +2. So that's what we're solving for, to be able to solve for K2. And what I would do is do a 2 times row 1 and add it to row 2. And that would give me a 0. -2 plus 2 is 0. -2 plus 2 is 0. So what does that tell me? That tells me that from this first line, I've got -2x1 minus x2 is equal to -1. And so if I solve for x1, that would be a positive x2 minus 1. And then dividing both sides by -2, x1 is equal to -1/2 x2 plus 1/2. All right, so we're going to choose just a nice value to make it friendly on us. How about it if I let x2 equal 2? Well, then x1 would equal -1. Oh, I guess I didn't make it that friendly, but oh well. All right, so I got x1 is equal to -1/2, and x2 is that. So that means my K2 is going to be -1/2 and 2. So that means your second solution is of the form e to the lambda t times K2 plus K1 times t. So x2 would equal e to the, my eigenvalue is -3, so -3t, times K2 was -1/2 and 2, and then plus K1 was a 1, -2, and then times t. Yeah. So that means x2 is e to the -3t times the matrix. I would go -1/2 plus 1t, and then 2 plus -2t. So there's your second solution. Isn't that nice? All right, so your homogeneous solution to the whole thing is the linear combination of your two solutions. So a C1 e to the -3t times 1, -2, and then plus C2 e to the -3t times -1/2 plus t and 2 minus 2t. There you go. Nice. All right, let's do another example. This time, my matrix is a 3 by 3. -2, 3, 3, 1, -3, -1, -1, 4, and 2. All right, so again, we're going to start off with lambda I minus A. And that would give me a lambda plus 2, a -1, a +1, -3, lambda plus 3, -4, -3, +1, lambda minus 2. All right, I don't have any zeros anywhere, and I don't know about you, but I would prefer to like zero something out. I notice I could take this and go, yeah, let's get rid of at least make one of them 0 just to help ourselves out. You can by all means find the determinant of this 3 by 3. You can totally do that too. But row 1 plus row 3 will at least zero something out for me. Lambda plus 2 and then a minus 3 will leave me with a lambda minus 1. Negative 1 plus 1 will give you a 0. 1 plus lambda minus 2 will give you a lambda minus 1. And then I'll just go ahead and leave everything else alone. Just try to save yourself some steps in doing that. And notice that now that I have a 0 here, I've removed one of the pieces of finding that determinant. So it helps out a little bit, not a whole lot, but all right. So my characteristic polynomial would be, let's see, it goes positive, negative, positive. So this row is still positive, negative, positive for the signs. All right, so we got a lambda minus 1 times the determinant of negative 1, 1, lambda plus 3, and then a negative 4. It's a minus 0 and then a plus lambda minus 1 times the determinant of a lambda plus 2, a negative 1, a negative 3, and a lambda plus 3. All right, so that gives me lambda minus 1 times, what is that, a 4 minus lambda plus 3. I'll need to distribute that negative sign in there. And then a plus lambda minus 1 times lambda plus 2 times lambda plus 3 minus a positive 3. Okay. What I notice is I've got a lambda minus 1 and a lambda minus 1. So I'm going to go ahead and factor that one out, if that makes sense. Hopefully it does. So I'm going to factor out a lambda minus 1 from both of the factors. Let's change this to a bracket here. And what I would be left with is a, let's distribute that. Okay, so a 4 minus 3. So a 1 minus lambda from this whole factor. And now I have also factored out this lambda minus 1 out front here. So I'd be left with what's there, which is a plus lambda squared plus 3 lambda plus 2 lambda, so a plus 5 lambda, and then a plus 6, but then a minus 3, so a plus 3. Now, by all means, if you want to make more work, go ahead, but I'm trying to be lazy. All right, here we go. Lambda minus 1 times, this would be a lambda squared plus 4 lambda plus 4. Well, that's a perfect square. That's lambda plus 2 quantity squared. All right, so now we've got our eigenvalues. Yeah, we got lambda equals 1, lambda equals negative 2, but that one's got a multiplicity of 2. All right, so let's start with the first guy. Lambda 1 equals 1. All right, when I plug that in, I would have a 3, negative 1, 1, negative 3, 4, negative 4, negative 3, a 1, and a negative 1. I'm going to solve. When are those 0? All right, so I want to zero these guys out, so that's nice. Row 1 plus row 2 will give me a 0, 3, negative 3, 0. Row 1 plus row 3 will give me a 0, 0. Ooh, 0 is 0. Very nice. All right. We need to do a little bit more. How about, I want to get rid of, I want this guy to be a 0. So how about row 2 plus 3 times row 1? All right, so 0 plus 3 times 3 will give you a 9. 3 plus negative 3 is a 0. Negative 3 plus 3 is a 0. And then 0 plus 0 is 0. And then you could leave these 3's, or since I haven't even written it yet, how about if I just do a 1/3 times row 2? Why not? 0, 1, negative 1, 0. Okay, so what does that give me? Well, first row is, I'll come over here. 9x1 is equal to 0. So x1 is 0. All right. And then row 2 says x2 minus x3 is equal to 0, which means x2 is equal to x3. So I would let x3 equal a, and then x2 is also equal to a, so that your first eigenvector would be a times, we got 0 here, and a 1 and a 1, which means that your first solution is e to the 1t times this eigenvector. All right, we got one solution. Now we need to go and find the other two, because there should be 3. Since it's a 3 by 3. All right, so now your second eigenvalue was -2, but remember it had a multiplicity of 2. So if we don't get 2 independent eigenvectors right now, then we got to do this process of finding the second one. Okay, so what do I get when I plug in a -2 into lambda I minus a? You'd get a 0, -1, 1, -3, 1, -4, -3, 1, and -4. Okay, so what am I going to do? I want, let's get rid of this 0 here. I'm going to go row 2 plus a -1 times row 3. That'll give me a -3 plus 3, 1 minus 1, -4 plus negative, plus a minus a -4, so 0, 0. And what else? I know this is weird, but I can also get this guy to be a 0 by just adding row 1 to row 2. 0 plus -3, -1 plus 1, 1 plus -4, and then 0. And then row 1 is staying the same. I don't have it in true row echelon form, but I don't care. All right. You don't care. Okay, so what does this give me? This gives me, or am I going to do more? No, that's good. Yeah. So row 1 says -x2 plus x3 equals 0, which just means x3 is equal to x2. Row 2 says -3x1 minus 3x3 is equal to 0. So x3 is equal to a -x1. All right, so if I let x1 equal a, then x3 will equal a -a, and x2 is also a -a. So that means k2 is, I'm going to go ahead and factor out the a 1, a -1, and a -1. Now, only one eigenvector. So that means we do have to do this process to find the third eigenvector. So x2 is e to the -2t. -2 is our eigenvalue, and then times 1, -1, -1. All right, so now we need to find k3. We need to find a third eigenvector that will satisfy the equation lambda I minus a times k3 is equal to -k2. All right, so that means I've got lambda I minus 1 was this guy here. So 0, -1, 1, -3, 1, -4, -3, 1, -4, times k3 is equal to the opposite in sign of k2, which was this guy, 1, -1, -1. All right, so now I'm solving. I can use augmented matrix of 0, -1, 1, -3, 1, -4, -3, 1, -4. Augment it with, we're solving K3 for when your coefficients are this guy, or your, not coefficients, but the answer column, right? So I'm going to distribute the negative in there. -1, +1, +1. Okay. How about if we're going to do the same thing again, right? We got row 2 plus -1 times row 3. And that'll give you a 0, a 0, a 0, and 1 minus 1, also a 0. I can get rid of this middle guy here by taking row 1 and adding it to row 2. And that would be a 0 plus -3, and a -1 plus 1, and then a 1 plus -4, and then a -1 plus 1. And then first row stays the same. All right, first row says -x2 plus x3 is equal to -1. So x3 is equal to x2 minus 1. And row 2 says -3x1 minus 3x3 is equal to 0. And so that one ends up being a add it, divide it, x1 is equal to -x3. All right, so if I let x1 is equal to a and x3 is equal to -a, right? And then x2, if this is -a, adding the 1 over, you'd have -a plus 1. All right, you're just going to choose some friendly numbers to plug into a. Yeah. So how about we do let x1 equal 0. Well, then x3 is going to also equal 0, but then x2 would equal 0 plus 1. Yeah, so that means your K3 is going to be 0, 1, 0. All right, so x3, remember, is e to the lambda t times K3 plus K2 times t. So x3 is going to be e to the -2 is my eigenvalue, -2t times K3, 0, 1, 0, plus K2, which was all the way up there, 1, -1, -1 times t. Yeah, so x3, I'll just simplify it, is equal to e to the -2t times 0 plus 1t, that's t, 1 plus -1 times t, so 1 minus t, 0 plus -t. Yeah? And so then your homogeneous solution is going to be the linear combination of x1, x2, and x3. So we got c1 times e to the t times 0, 1, 1, plus c2 times e to the -2t times 1, -1, -1, plus c3 times e to the -2t times t, 1 minus t, -t. And there you go. That's it. One little refresher, because on one of your homework problems, you're going to need synthetic division. So let me just do a quick synthetic division. Do you remember? If you got something like lambda cubed minus 4 lambda squared plus 5 lambda minus 2, how the heck do you factor that, right? Do you remember you would need to figure out your possible rational roots. Possible rational roots come from factors of the constant over factors of the leading coefficient. Right, so 2 is your constant, 1 is your leading coefficient, and so plus or minus 1 and plus or minus 2 are going to be your possible rational roots. And in algebra, you would start with 1 and plug it into synthetic division and see if it's a factor or not. See if it's a root. And so you plug in a 1. You only include the coefficients, which are 1, -4, 5, and -2. Leave a space. Bring down the 1. 1 times 1 is 1, right there. Plus -4 would give you -3. -3 times 1 is -3. Adding it to 5 is 2. 2 times 1 is 2. Adding it to -2 is 0. Yay! When you get a 0 as your remainder, then 1 is a root, which also means that lambda minus 1 is a factor. 1 is a root, but lambda minus 1 is a factor. And then these are the coefficients on your depressed equation, where you started with a lambda cubed, which means this would be a lambda squared, this would be a lambda, and then that's your constant. And of course, then that is easy. Quadratics, you know how to factor. And so how does this characteristic polynomial, this cubic factor, we got lambda minus 1, and then times two numbers that multiply to 2 but add to -3. That would be here, I'll write it first, -3 lambda plus 2. That's what you just did by doing the synthetic division. And then, of course, these two guys factor as lambda minus 1 and a lambda minus 2. And so you've got a multiplicity going on there. Just a little refresher, just in case you didn't remember how to factor a cubic. That's how. All right. Have a fantabulous day. Bye.